Welcome back. Here is one more example of determining how to compute area between polar curves. We're going to try to find the area that lies both inside the circle r equals 3 cosine theta and inside the limacon r equals 1 plus cosine theta. I've included a graph from Desmos of both of the polar defined curves. And the green one represents the circle. You'll notice it passes through the point angle 0 with radius 3 and the point angle pi over 2 with radius 0. That's how we're coming up with the circle you see there. It actually rotates through twice in that time period. And also we have the limacon, that's the red curve. When I want to look at the area that's both inside the circle and the limacon, the area I'm looking at is this area right here. That's the area I want. Now what we have to remember is that when we look at polar area, it's all based on the way we sweep it out. Let's go ahead and look at this straight in Desmos, and I think we can make sense of it that way. So I created this Desmos page to help make sense of this. Let me zoom that in a little so we can see all of it. And on the left-hand side, you'll be able to see this page later. We can look at what's happening here. So I'm going to annotate on this page for a second. So recall that we could start out by, we might want to know these 2 points of intersection, right? We have the curve 1 plus cosine theta. We want to know when is it equal to this curve 3 cosine theta. I'm going to subtract a cosine over, so we get 1 equals 2 cosine theta, and therefore 1/2 is cosine of theta. And I recall the angle whose cosine is 1/2 would therefore be pi over 3. And that also will be true for negative pi over 3. So I now know that these 2 points of intersection are positive and negative pi over 3, okay? We remember that when we're looking for area, polar area, what we want to do is think about rays sweeping out. So notice that if I were to sweep out between these 2 rays, which part is going to be that part inside that I was really looking for? Remember, we were really looking for all of this area, the part that landed inside both curves. Well, what you might notice is that between pi over 3 and negative pi over 3, that actually is solely the area being spread out just by going to the limacon from negative pi over 3 to pi over 3. So I'll show you that here. So here I've turned on, what you've got in this folder is the first part. The green part represents the part that's less than the limacon, so the part that's inside the limacon and swept out between negative pi over 3 and pi over 3. Whereas the brown part, and here I can turn this off and you can see the difference between them. The brown part right now, this is the whole region all the way to the circle. And so we see that if we go all the way to the circle, we've gone too far. We actually aren't looking for an area between curves if we just want this region. To get a good portion of the area we're looking at, it would be enough just to find the integral that would compute the area inside the limacon swept out between negative pi over 3 and pi over 3. So let's go over to my presentation screen, and we notice that we're going to have 2 parts here. So the part that's only in the limacon, that was the part that goes from negative pi over 3 to pi over 3, so that's going to be 1/2 negative pi over 3 to pi over 3. We want the square of the function determining the radius, so that's 1 plus cosine theta squared d theta. Now let's go back to Desmos and figure out what the rest of it is. Now the other part of the region inside both the circle and the limacon is this part. But notice that part, those 2 pieces, those are portions that are both just inside the circle. And in this case, we actually can see we have a lot of symmetry going on here. So we could just find this top region and then double it. But if we wanted to actually represent the integrals for all the pieces, I'll show you how to do that as well. So there, we have that region we've already taken care of. We already have an integral that gives us that region. Then this is the part, the next part. So we notice if we want to go inside the circle all the way to the origin here and collect that little sandwich, it turns out that we go all the way up to Lima on it, sort of be the wrong part, but that what I want this bed in here. That if I want the region swept out along the ray on the circle, starting at pi over 3, that was that intersection, then going all the way till the point where I hit the origin, well, that corresponds to pi over 2 because the cosine of pi over 2 is 0. So that means our next integral would be, in the circle, I'll put top half, would be the integral from 1/2 from pi over 3 to pi over 2 of 3 cosine theta, that circle squared d theta. And then if we go back and we want that other region, the one that's down here in the bottom, well, we have to find the next point where we're going to be going from the origin to the ray where negative pi over 3 is. So negative pi over 3 is also the same thing as positive 5 pi over 3. And I'm reading back from there to the next point where on the origin we would have cosine theta be 0. Well, recall that cosine theta equals 0. Cos theta equals 0, and so does 3 cos theta, when theta is equal to pi over 2 or 3 pi over 2. And so to get this region, what I want is to take the integral 1/2 from 3 pi over 2 to 5 pi over 3 of 3 cosine theta squared d theta. And that's going to give me the lower part. So I'll show you what that looks like all put together because I've got all of them in here. And so that's the region I'm looking for, those 3 areas. And none of these is a very hard integral to do. But again, these two are equal, so I could just double one of them. And there you go. I'll write out the full work for the solution to this in a separate slide and I'll post it.